Hello, my name is Wayne Delker. As you read in my bio, I got my PhD in chemistry in 1981 and split my career between working with GE Plastics and Silicones and the Clorox Company, retiring from Clorox in 2015 as the Chief Innovation Officer and Senior Vice President of R&D. Throughout my career, I've always been very interested in how to synthesize and use polymers to solve real problems. And after I retired, I came across this technology that you're reading about now that I'm extremely excited about. And I really want to talk now about the performance of that system. First, it really gives the consumer a lot of options of how much caffeine they can take in their coffee. Right now, they can either have caffeinated coffee or decaf. They really have no control. Second, it allows cafes who currently need to carry both caffeinated and decaffeinated to simplify their product line, as well as have a much wider variety of decaffeinated coffees available to their consumers. Third, it allows sensitive consumers like myself to have that extra cup of coffee in the evening because you love it, because of the taste, without worrying about having too much caffeine and not being able to sleep that night. So we think this is a really big deal for our consumers that love drinking great coffee. What we've been able to accomplish, and what I'm going to talk about, is we've synthesized a unique, what we believe one-of-a-kind polymer system, which we have patent coverage on, that has shown to take out greater than 70% of the caffeine from coffee at the point at which the consumer drinks the coffee in less than 1 minute. This has never been accomplished before, and it was technically extremely challenging, and we think represents a significant breakthrough. We've called this technology programmable polymers, and the reason for that is we believe, and you'll see some results in a minute, that by changing how we make the polymer, we can really fine-tune it to provide a lot of different properties. So it's almost like how you would program a computer to do whatever you need that computer to do. We have that same sort of control over this polymer. There's been no prior example of this being used in consumer technology, although many people have tried for decades. And in fact, it was very challenging for us. It took a team of chemists and engineers with over 100 years of combined experience working over a decade on this problem to create the breakthrough I'm about to tell you about. Finally, while removal of caffeine is our primary objective here, the technology I'm going to tell you about is so flexible that we think it could be applicable to a variety of different medical and consumer problems where you need to take out one molecule selectively from a solution. Next, I'd like to describe a little bit how it works. Basically, we start with a template, which in this case is the caffeine molecule, and then we surround that with functional monomers. The template and the monomers then form a very stable complex. At that point, we initiate polymerization, locking those functional groups of the monomers in place. After the polymer has been stabilized, we then extract out the caffeine, leaving a hole perfectly constructed to fit the caffeine molecule. When that hole then encounters a new caffeine molecule in a cup of coffee, it very selectively reinserts caffeine into the cavity, pulling that caffeine out of solution without any residue or any materials from our polymer going into the coffee itself. So it's totally safe. The first thing we needed to do is really test how well this worked. And what we ended up doing is, of course, tested it in our labs in collaboration with McCampbell Analytical, a well-respected third-party analytical facility. But everything I'm going to show you has also been confirmed at Clemson University in South Carolina, and then recently has been tested by a leader in the consumer coffee business in their own labs. As you can see from this chart, in all three places, and we use an 8-ounce Pike's Place cup of coffee as our standard, in all three of these labs, the percent caffeine removal was almost identical, roughly 70% within experimental error. These results, done in different times, different polymers, different locations, gives us the confidence that the phenomena I'm describing right now is real and is reproducible. The next thing we wanted to determine is how far could we push our technology. So we started using additional amounts. And you can see in the first row there, we were able to actually get our technology to remove 94% of the total caffeine in that Pike's Place coffee, which is very similar to a commercially decaffeinated cup of coffee. So the technology is capable of really removing large amounts of caffeine as we had hoped. It was also important for us to understand how robust and reproducible the polymer is. So what you see here are 7 batches of independently prepared polymers where we then measured the caffeine removal. And as you can see, once again, extreme consistency from batch to batch, giving us the real confidence that as we scale this up into large scale, we'll be able to have a very robust process. So far so good. We also really wanted to see what would happen if we continued to do successive treatment of coffee with our polymer. And here you can see if we treat with a 3-gram amount, we remove 39%. But if we retreat it again in a second removal step, we took that to 72%. And again, then if we did it with excess of polymer, we could take it to 94% caffeine removal. What's important from this result for us is that by adjusting the amount of polymer that we use in the application, we can actually fine-tune the amount of caffeine removed, which we think is going to be a major benefit to the consumer and will allow us to offer a whole range of different products. On this slide, I really wanted to show kind of how we went about testing selectivity. As you recall, selectivity of removing caffeine is a fundamental element of this system. And you can see the caffeine structure on the left. Theophylline, which is in the center, is almost identical and varies only by the absence of a methyl group on nitrogen. That is the component in coffee that is as close to caffeine as we can get, and we wanted to understand if we could selectively remove caffeine. Also on the right-hand slide is chlorogenic acid. Very different structure, but also one of the major components of coffee. So we wanted to see how caffeine could be removed in the presence of chlorogenic acid. Well, here's the data with theophylline. Again, you've seen the same protocol before, so I won't go into details, but you can see we can actually remove up to 94% of the caffeine, only removing 14% of theophylline from that coffee. As you think about the similarity of the chemical structures, this is really a very amazing, almost a surprising result, which shows how perfectly formed our cavity is towards the caffeine molecule. Here we're looking against chlorogenic acid, and once again, you can see very similar results. Removal of 94% of the caffeine, and again, only about 16% of chlorogenic acid removed. So once again, these two charts together show that we have the ability to remove caffeine against, when compared to very, very similar molecules, but also remove it selectively when in a solution with chlorogenic acid, at far greater concentration. One of the things we're working on now is continuing to improve this polymer to make sure that we have minimal change in color, odor, and taste as we go through this process. In summary, we feel we've created a very unique material that meets all of our design criteria in allowing the consumer to take charge of their caffeine removal and their caffeine consumption with less than a minute, with a simple stirring process, remove that caffeine at a point of use. Thank you for listening, and what I would like to show you next on the next video is a little bit of the technology journey we took and how to develop this technology, as well as share our intellectual property strategy going forward. Thank you.